If we look at the selectivity for the bromination reaction, however, the secondary position is favored in a 97:3 ratio. In this video, we're going to look at the selectivity of the radical halogenation reaction. Why can we do this reaction selectively with bromine, but with chlorine, the reaction doesn't work so well? To answer that, let's look at this halogenation reaction of propane with generic X2. When we do this reaction, we can actually form one of two possible constitutional isomer products. We can either form the secondary product with the secondary alkyl halide, or a product that forms a primary alkyl halide. There are two different constitutional isomers we could form. Now, if we ignore everything about chemistry and chemical stability and just look at this reaction based on numbers and statistics, if we look at the starting material, there are 8 total hydrogens in this starting material. 6 of them are on primary carbons and 2 of them are on the secondary carbon. If we look at the product distribution then, for these 8 hydrogens, for every 8 reactions, statistically we would expect 6 of those reactions to be at the primary position, 6 of 8 times, and 2 of those 8 reactions to be at the secondary position. So the ratio, the product distribution we would expect is about a 25-75 ratio. 2 out of every 8 reactions at the secondary position, 6 out of every 8 reactions at the primary position. This is not what we actually see because we're not just based on statistics, we're actually based on chemistry and chemical stability. So what are the actual product ratios? Well, it depends whether you're doing the chlorination or the bromination reaction. With the chlorination reaction, the actual selectivity is about 60% for the secondary product and 40% for the primary product. So not at all what we would expect from statistics alone. The secondary product is actually a bit more stable than the primary product, but this selectivity is fairly close to 50-50. It's fairly close to a 1-to-1 ratio of the two products. And so this reaction really is not very selective, and we don't really use this reaction very often. If we look at the selectivity for the bromination reaction, however, the secondary position is favored in a 97:3 ratio over the primary position. This is very good selectivity. We can do the bromination reaction selectively. Why is this? Why is the bromination so much more selective than the chlorination? To answer that question, we need to look at the selectivity-determining step, and the selectivity-determining step in this reaction is the first propagation step. So if you recall, the first propagation step is where the alkane reacts with the halogen radical to do the hydrogen atom abstraction, to form the carbon radical. So we can form one of 2 possible carbon radicals. We can form the secondary carbon radical or the primary carbon radical, and we will form HX, our byproduct, in this first propagation step. This is the step that determines the selectivity of the reaction. Specifically, it's the stability of the halogen, whether it's Br dot or Cl dot, that determines the selectivity of this reaction. So what's the difference between Br dot and Cl dot? Why is one more stable than the other? It has to do with the size of the element and therefore the size of the orbitals. Bromine is lower on the periodic table. Bromine has larger orbitals. It's a larger atom. So the radical electron is more stable in the larger atom than the chlorine radical. The bromine radical is more stable than the chlorine radical. Why does that mean that the reaction is selective for bromination, not chlorination? Before we answer that, let's pause for a second and recall Hammond's postulate. Hammond's postulate says that the transition state of a process resembles the species to which it is closest in energy. If we look at an exothermic versus an endothermic reaction, an exothermic reaction has what we call an early transition state. The transition state and the product are similar in energy and therefore similar in structure. The transition state looks most like the reagents. The stability of the transition state is governed by the stability of the reagents. That's a really important point. Keep that in mind. We'll come back to that later. Stability of the transition state is governed by the stability of the reagents for an exothermic step. For an endothermic step, the reverse is true. The transition state and the products are similar in energy and therefore similar in structure. The transition state is most similar to the products in an endothermic step, and therefore the stability of the transition state is governed by the stability of the products. Again, that's really important. We'll come back to that later. The stability of the transition state is governed by the stability of the products. This is Hammond's postulate. The transition state is closest, it looks most similar to the species to which it is closest in energy. What does that mean for our reactions here? Well, let's look at energy diagrams for this first propagation step for bromination and for chlorination. We'll start with chlorination. We'll draw an energy diagram for this first propagation step for chlorination. The chlorine radical is less stable than the bromine radical, so the chlorine radical starts fairly high in energy, and it's reacting with propane. We're forming 2 possible radical intermediates. Because we are actually using chemical stability, the secondary radical we know is more stable than the primary radical. So on a reaction coordinate diagram, the primary radical would be, I'm just going to make this up, approximately here, along with HCl byproduct. And the secondary radical in terms of energy would be about here, along with HCl byproduct. So our energy diagram for this reaction then we would have some kind of activation energy to form the primary intermediate, and we'd have some kind of activation energy to form the secondary intermediate. What I want us to focus on is the activation energies for these steps. There is some activation energy to get to the primary radical, carbon radical, and some activation energy to get to the secondary radical. What's important here is the difference in the activation energy, what we can call delta EA, the difference in the activation energy. For an exothermic process, the stability of the transition state is governed by the stability of the reagents, and we're using the same reagents for both processes, so the stability of the transition state is fairly similar. There's not a lot of difference in the activation energy for these steps. Because there's not a lot of difference in the activation energy, neither process is significantly easier than any other process. There's not a lot of energy difference, so there's not a lot of selectivity difference. If we look at a similar reaction coordinate diagram for the bromination reaction, the bromine radical is more stable than the chlorine radical, so the bromine radical starts out lower in energy and is still reacting with propane. We're still forming a primary radical and a secondary radical, and those have the same stabilities that we saw before, and we're still forming, in this case, I guess, HBr as our byproduct. So now let's look at the difference in these two steps. This is now an endothermic step. So the reaction from the bromine radical to the primary radical has some kind of activation energy, and the reaction to form the secondary radical also has some kind of activation energy. Again, we have a activation energy to form the primary product and a activation energy to form the secondary product. But notice what happens with the difference in the activation energy this time. The stability of the transition state is governed by the stability of the products for an endothermic reaction. And here we're forming very different products. The secondary radical is much more stable than the primary radical, so the transition state to form the secondary radical is much more stable than the transition state to form the primary radical. That means there's a large difference in the activation energy for these two processes. This large difference in activation energy means it's much easier, much faster, and therefore more selective to form the secondary radical than it is to form the primary radical. This is the reason why the bromination reaction gives us a 97.3 selectivity, and the chlorination reaction only gives us a 60.40 selectivity. This difference in activation energy for this first propagation step is that reason. There is a large selectivity when there's a large difference in activation energy, and there's a low selectivity when there's a low difference in activation energy. This is why we can have different selectivities for these reactions. It also explains why the reaction doesn't really work well for fluorine and iodine. Iodine is even more stable than bromine, and so there's an even larger activation energy, and actually that activation energy gets so large as to be almost impractical. It's much slower, much harder to do an iodination than a bromination. Fluorine, on the other hand, is much, much less stable than the chlorine radical, so much less stable that this process becomes so exothermic that, first of all, there really isn't much selectivity at all, but secondly, it's so exothermic that if you actually tried to do the fluorination in lab, you would probably burn down the lab. It's so exothermic. So we really shouldn't do the fluorination reaction. The chlorination reaction is exothermic and therefore unselective. The bromination is endothermic and therefore selective. We can do the bromination reaction selectively, but not the chlorination reaction selectively.
Thanks for training with us today, Ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.